record this. So it's sessions for anyone who wants to learn something about modeling and who is really beginner in this. We already did 3 previous sessions. So the first one was about what are models and why are they useful. The second one was about activated sludge models. And then we had a session about sedimentation models. All the sessions are recorded and posted on YouTube afterwards, so you can always look back to them, or if you miss a session, you can just watch it after the session. Today's session will be about physico-chemical modeling, and our speakers today are Kimberly Solon and Helene Haddouk. So I'll maybe first let you introduce yourself, and then you can start today's session. So maybe, Helene, you can start to introduce yourself if you can.
Yes, sure. Thanks, Luz. Hello to everybody. So I'm Hélène Haddouk. I'm senior process engineer at Dynamita since 10 years now. So at Dynamita, we are developing simulation software packages for wastewater and water processes. And so those software names are respectively Sumo and Dynamizo, which has been freshly released this morning. And maybe plus that I'm at Dynamite, I'm in charge of developing the biokinetic models, all the implementing all the biological and physical-chemical reactions in the model and maintaining them. So that's my expertise.
Okay, thank you. And Kimberly?
Yeah. Hi, everyone. My name is Kimberly Solon. I am from Ghent University in Belgium. I'm a postdoctoral researcher, and I worked a lot before with plant-wide modeling, mechanistic modeling, and the past few years also with data-driven modeling. And I've also worked with control of wastewater treatment processes. Yeah. So yeah, I would like to start now the session on physical-chemical modeling. So it will be composed of 2 parts. So the first part, which I will be talking about, is mainly on the topics and concepts of physical-chemical modeling. So it will build up on that, and then Helene will also show more concrete example, more fun examples on how this has been used in wastewater treatment processes and wastewater treatment modeling. So let's start with the fundamental question. So why do we actually need physico-chemical models? That is because not everything in wastewater treatment is biological or biochemical. So on the left here, we see biochemical processes. These biochemical processes are all mediated by microorganisms. For example, bacteria that converts ammonia to nitrate, they produce methane, they can also reduce sulfate. And this is what most people think when they talk about wastewater treatment modeling. But looking at the right side, so this is a figure of the physical-chemical reactions that also happens spontaneously. So this physical-chemical reactions, there are no microorganisms required. So for example, CO2 transferring to the gas phase, calcium and phosphate forming solids, and iron species changing oxidation states. And critically, these 2 kinds of reactions are actually interacting. So biochemical reactions and physical-chemical reactions. Biochemistry produces the compounds, and the physical chemistry determines the speciation of these compounds and their fate. So if we only model the biochemical reactions, we actually miss half of the story. So that's why we are here today, to understand how to model this physical-chemical side. So what are physical-chemical processes? So as I mentioned, they are spontaneous reactions in the sense that they don't require microorganisms. So they usually happen across 3 phases, so the gas phase, liquid phase, and the solid phase. And there are basically four main types. So the liquid phase reactions or aqueous phase chemistry. So these are the ion pairs, the acid-base reactions, and then we have the liquid solid phase, which is the precipitation and reduced solution. We also have the liquid gas phase, which is gas-liquid transfer. And then additionally, we have oxidation and reduction reactions. So one thing that I would like you to notice is the fourth column, the speed. So the speeds of these reactions are also varying a lot. Among this, the liquid phase reactions, so the aqueous phase chemistry is almost instant. So they are in millisecond almost. On the other hand, precipitation and dissolution, so the liquid solid phases, they can take minutes to hours. And this speed difference is also important, why we need different modeling approaches when we want to incorporate physicochemical process in wastewater treatment modeling. So now let's go a bit deeper into the liquid phase chemistry. So we actually model physicochemical reactions because the wastewater treatment modeling goals is also evolving. So before, with the traditional activated sludge models, we could predict and simulate simple pollutant removal goals. We can also adjust them so that we can also calculate and predict or simulate efficiency goals. And more currently, we are now also more focused on sustainability and having these multiple goals. For example, resource recovery, carbon neutrality, avoiding greenhouse gas emissions. So we have so much more priorities, and the questions that we are asking before have also evolved. So for example, new questions that wastewater treatment plants are also asking are, for example, can we optimize pH to maximize ammonia stripping? How can we maximize recovery of phosphorus with minimal use of chemicals? Can we minimize energy while capturing biogas and at the same time avoid greenhouse gas emissions? Can we also chemically oxidize H2S to elemental sulfur instead of going until sulfate so that we don't lose elemental sulfur to water? And actually, every single one of these questions requires understanding the physicochemical processes that are on this table. So we need to know the liquid chemistry to understand the pH, which is important for precipitation, which is also important to understand gas transfer and oxidation reduction. So we cannot answer these questions if we only use biochemical models, and we need physicochemical modeling for that. Now, one crucial principle in aqueous phase chemistry is chemical equilibrium. This is quite basic, but I want to go back to this as well. So liquid phase chemistry modeling depends heavily on the chemical equilibrium theory. Why? Because liquid phase reactions in wastewater are very, very fast. So as I said, milliseconds. So that within any practical wastewater time frame, these reactions are always at equilibrium. And any reversible reactions, so for example, reactants A and B, which are forming products C and D, this always occurs in both directions simultaneously. And at equilibrium, these rates of the forward and backward reactions are balanced. So there's no net change in the concentration. And this equilibrium state is mainly described by the equilibrium constant K. So the equilibrium constant K is the products over the reactants. But I also want to put your focus or your attention to the squiggly brackets. So we are actually using activities instead of concentration. So we use curly brackets to denote activities. This is because activities take into account the non-ideal behavior in real wastewater. We will also come back to the concept of activities later on. And for wastewater, the most important type of chemical equilibrium is acid-base equilibrium. So an acid releases a proton, the H+, forming its base. So some common examples of chemical equilibrium and very important in wastewater is the ammonium equilibrium. So at low pH, it's ammonium, which stays in water. And at high pH, we have ammonia, which can also be stripped away. So it's important for if you want to model toxicity and gas stripping. The carbonate system, which we all know is very important for the pH. So the carbonate system controls the pH in every biological reactor in the wastewater. And so this is important for pH control, and also it's important when we want to model gas transfer properly. And then we also have sulfide. So we see that at low pH, we have hydrogen sulfide gas, which is toxic and corrosive, but at higher pH, we can actually keep it in solution. So modeling this is also important to take into account, corrosion, toxicity. So if you can see the pattern here, the pH determines which form exists, and that determines everything. So it's related to toxicity, to gas transfer, and also to precipitation. Now, another concept in liquid phase chemistry is ion pairing. So actually, the acid-base equilibrium that I showed you before is a special case of ion pairing. So in acid-base equilibrium, we know that it's an acid-base equilibrium if it involves the protons, if we have the H+. On the other hand, ion pairing is similar to that, but it can involve any ion. So it's pairing with any other ion. So one cation with an ion. So both of these are equilibrium reactions. So ion pairing is also important in wastewater modeling. Another important concept that is important when we want to model physical chemistry and for wastewater treatment is the difference between components and species. So we want to differentiate between the two because the biology, they often react with a specific species, but not the total component. So a component is actually what we can measure in the lab. So usually it can be the total amount. So this is from the lab analysis. So for example, is total ammonia nitrogen. So for example, we measure in the lab 100 milligrams per liter of total ammonia nitrogen. On the other hand, we have species. Species are the individual chemical forms. And all those species can also be analyzed in the lab. We can also calculate the species from pH and equilibrium once we know the component. For example, we have ammonium ion and free ammonia ion, let's say 80 and 20 milligrams per liter respectively. What is important here is that the total 100 milligrams per liter is equivalent to the total ammonia nitrogen, which is the component. So the sum of the species must add up to the component. Now, since we can have a lot of components and therefore a lot of species in our wastewater, it's important that there's a way to organize all our equations systematically. So we actually use what we call the tableau approach. So it is a matrix wherein the species are written in the rows and the components are in the columns. And so how do we make this tableau approach? So we list all the components. So we have it in each of the column. And then we build a matrix of how the components make the species. So the species will be in each of the rows. And then the computer can solve this matrix algebraically. So to be more specific, so the mass balances, they are coming from the component. So we write one mass balance for each component. So for example, the component inorganic carbon, so SiC. So the component is actually the sum of all the inorganic carbon species. In this case, we can see that so inorganic carbon is carbonate, so CO3 2 minus, and then we have HCO3 minus plus CO2, and then we have sodium carbonate, and then we also have NaHCO3. So then we have the mass balance just for the inorganic carbon component. And we have to do the same for all the components, so until the sixth one here. But this is just like a very small example, but you can also have lots more components, therefore also more species. And then for the species, we can make one equilibrium equation for each of the rows, so for each of the species. We just have to read across the row, and we use the numbers that are here, so the coefficients here as exponents. So for example, the row for acetic acid has, this is H plus, so H plus times acetate ion times the equilibrium constant. And here, notice that for the equilibrium equation, we have to use the curly brackets. So it means that for the equilibrium equations, we have to take into account activities. So here, for this small subset, so for this small table here, we actually have 6 components and then 15 species. And then this will actually total into 6 mass balances and 9 equilibria. And this can be all automated from this one table, and this Tableau approach ensures that we don't miss any equations. Okay, going back to the activity concept. So in real wastewater, we actually must use activities and not just concentrations. So what is activity? So activity is in formula, it's just gamma times the concentration, where gamma is the activity coefficient. So it's like a correction factor. It's a correction factor for the non-ideal solution that we have. If we have a pure water, then our activity coefficient will be equal to 1. But since we work with wastewater, we know that we don't have ideal conditions. And yeah, we have to always use this correction factor or activity coefficients. Looking at these graphs on the right, so the x-axis is the activity coefficient, and the y-axis is the ionic strength. So the ionic strength actually represents how concentrated your solution is with ions. So the more ions you have, so the more stronger your wastewater is, the higher the ionic strength that you have. I showed these 2 figures here to also differentiate between a monovalent ion such as sodium, so it's just Na+, versus a divalent ion, which is magnesium 2+, so a divalent ion. So if we look at the orange line, so the yellow line, so at the same ionic strength, we can already see that activity coefficients vary between the two. So for a divalent ion, such as magnesium, your activity coefficient is, let's say, around 0.4, while for the sodium ion, a monovalent, it's around 0.7. So we are the more ions that you have, the stronger the ions that you have, the farther you are from ideal conditions. So similarly, if you have higher ionic strength, so the orange line here, at the same ionic strength, the activity coefficient is also much different. So why is this important? Why does this matter? So it has a very high implication for wastewater. So low strength wastewater, what is low strength wastewater? It's the common domestic wastewater. So domestic wastewater is usually up to 0.1 molar. So this, the orange line that I showed you here, and we can already see that even at low strength wastewater, the activity coefficients are significant. So we already see that our ions behave as if they are less effective than they really are. So how much more if we talk about anaerobic digester, or if we talk about industrial wastewater? So they are much farther than ideal conditions. And if we ignore activities, if we use concentrations instead of activities, our equilibrium equations will be wrong because, as I mentioned, equilibrium equations should use activities instead of concentrations. Therefore, if you also don't use activities, your pH prediction will be wrong. Therefore, your prediction of precipitation will also be wrong. So for a more accurate wastewater modeling, especially for high strength wastewater, activity corrections are not just optional, they are essential basically. So how do this relate to activated sludge models? So these liquid phase reactions, wherein we calculate the activities of all the species that are present, these are recalculated every time step through a set of algebraic equations after the biological reactions update the concentrations. So the activated sludge model, you will have the concentrations there of your components, and then the physico-chemical model calculates the activities of the species for each time step, and then it will give back to the activated sludge model, for example, the pH, the activities, the concentrations of the species. So before I showed you how we calculate the ion activities. So as I mentioned, these are important to predict how solids form, so precipitation. So the liquid phase chemistry is also very much related to the solid liquid phase chemistry. So we need first this aqueous phase chemistry to also be able to make models of precipitation. So precipitation is when dissolved ions come together to form solid particles. Precipitation is both good and bad in the context of wastewater treatment. So it can remove nutrients, so we can recover resources such as struvite. But precipitation can also cause cloggings in the pipes. It can form scales in the pipes. Now, when the precipitation occurs? So we always have dissolved ions in our wastewater. Now, once you have a lot of these dissolved ions, so your solution will become super saturated, and then your precipitate will form. So some common and very important precipitates in wastewater are struvite. So struvite, before it was, we always talk about struvite for due to that it's the one that causes cloggings in the pipes, especially in the sludge line. But now we'll talk more about struvite in the context of resource recovery, because I think it's one of the most common fertilizer products that you can recover from the wastewater. Calcium carbonate is also a common precipitate that causes scaling as well. And then iron phosphate. So this is the precipitate that is formed when you are doing chemical phosphorus removal. So when you are using iron chloride salts in the wastewater, so you can also have aluminum phosphate when you're using aluminum salts for chemical phosphorus removal. Then you can also form metal sulfide precipitates if you want to remove heavy metals using sulfides. So this slide summarizes how precipitation and dissolution work from a thermodynamic and kinetic point of view. So at the simplest level, precipitation is just oppositely charged ions coming together. So A plus and B minus, so cation and an ion forming a solid AB. Whether that's solid, whether that AB actually forms or not, depends on the solubility product constant. So a constant KSP, which you can find in literature and also in some software. To check if precipitation will occur, we actually compare this solubility product constant with the ion activity product. So the ion activity product is simply the product of the activities of the dissolved ion. So this is again where the liquid phase chemistry is important and the concept of activity. So the ion activity product in comparison with the solubility product constant determines if we will have a precipitation or not. So we can have three possible states: undersaturated, saturated, or supersaturated. So when we have supersaturated state, so when our ion activity product is greater than our solubility product constant, so that's when precipitation occurs. So precipitation becomes thermodynamically favorable. And on the right, you see what actually happens once the solution is supersaturated. So once precipitation occurs, so first you have nuclei that are forming either on existing surfaces or spontaneously in the solution. And then this nuclei grow into crystals or crystallites, which can aggregate and settle and transform through an aging process into more stable mineral phases. So you can see there's like a step wherein precipitation happens from a nuclei to a mineral. So here you can actually see that precipitation takes time. From the initial equation, it seems that it's like the equilibrium equation that I showed before. So one might think that they look instant, like acid-base reactions, but in reality, precipitation takes time. So yeah, maybe I could give you a few seconds. So my question to you is, what do you think controls how fast precipitation actually happens? So actually, I have already in mind like pH, temperature, mixing, surface area, and impurities. What do you think happens to the precipitation speed when you change these different factors? So for example, if I increase the pH, will my precipitation be faster or slower? When temperature is increased, what happens to the rate of precipitation? If I steer more intensely, what happens to precipitation speed? What if I have bigger surface area, or initial like surface particles that are present there? What if there are also impurities present? Will my precipitation be faster or slower? This is quite different things. For example, for temperature, when our temperature is higher, our precipitation speed is faster. For the pH, when we have a higher pH, for most metal hydroxides, carbonates, and phosphates, we can have a higher precipitation speed as well, but it always depends on the type of precipitate. Mixing can also go in both ways. So if I steer more intensely, you can improve at which your ions come in contact with each other, so you can promote precipitation. But then when you have sensitive crystallites that have just formed, they can also disassociate again. Surface areas are normally, when you have higher surface areas, you will also have faster precipitation speed. Impurities, it can also go in both ways. So impurities can act as seeds for the crystals, so it can improve precipitation speed, but it can also block the growth of some crystals, so it can also slow down precipitation speed. But all of these factors affect the speed of precipitation. Therefore, even if you have the same supersaturation, precipitation can be slow in one system and extremely fast in another. So as an example of the modeling approach for precipitation and dissolution, so taking into account, for example, calcium phosphate. So first we calculate the activities, but this is actually calculated from the aqueous phase chemistry. So we calculate the activities of the individual species, so the calcium and the phosphate. And then we calculate the ion activity product. So this ion activity product can be calculated at every time step. And at every time step, you can also compare it to the KSP. And in this case, what do you think will happen? Will we have precipitation or no precipitation? So undersaturated or supersaturated? So here our IAP is higher than our KSP. So if that's the case, we have supersaturated, therefore we have precipitation. And so we know that there will be precipitation, we just don't know yet how fast it will be. And the rate, this is just one equation, one example of equation how we model the precipitation rates, but there are also other forms of this precipitation rates. So it depends on the kinetic rate constant, the surface area, and the supersaturation degree. And since, as I mentioned, the rates of precipitation compared to the aqueous phase chemistry is much slower. So this it's not instant, it can take up to minutes to hours. So we have to use differential equations, unlike for the liquid phase chemistry, wherein we can use algebraic equations and we can just solve everything algebraically simultaneously. So to summarize all of these concepts, so physical-chemical reactions are spontaneous. There's no microbiology needed. Liquid phase reactions are very fast. So we can represent them as algebraic equations. We can use the tableau approach to make everything organized and systematic. Activity corrections are needed for concentrated solutions such as wastewater. And pH is calculated and not fixed. On the other hand, precipitation is a slower process compared to the liquid phase reactions. So the kinetic processes needs rate equations, and precipitation rate depends on the supersaturation or the degree of supersaturation. And everything is connected. So the liquid phase reactions are related to the liquid solid phase reaction. So pH affects speciation. So the speciation affects also the precipitation. Precipitation affects pH. Thus, all of these have to be solved together. So there are much more information available in the book. Actually, it's a scientific and technical report number 29. So the generalized PCM for wastewater treatment processes. This is an open source SDR from the IWA. So I would now pass it on to Helene for her presentation.
Thanks, Kimberly. That was a great introduction to this very complex topic that is physical chemistry. Can you see my screen? Maybe no.
It's loading right now.
Come.
Yeah, we can see it.
And okay, then I will continue following Kimberly to illustrate what she already presented for most of it. And I will especially show how all this interact together with the pH, how the biology affect the pH and the pH affect the biology, how it affect the gas-liquid transfer and vice versa, and precipitation, dissolution, and chemical treatments too. So we will start with the biology. You may know that some organisms are sensitive to the pH. And as an illustration here, there is a graph. Maybe I will use this pointer. This graph is coming from this book, which is also open source and a great source of information for our field. And this is a graph depending on the pH, which show the fraction of the growth rate of nitrifiers compared to the maximum growth rate that the nitrifiers has at 7.2 pH. So we can see that this growth rate just dropped around pH 6, 6.5, and around pH 8.59. So the biology is affected by the pH, but also the biology affects the pH, and especially the nitrification process, which reaction is written here, and the oxidation of ammonia into nitrate produce some acidity. Here, for 1 mole of nitrogen ammonia, it produces 2 mole of protons. Then nitrification is often comes often with the nitrification process, which is the reduction of nitrate into N2. And this reaction will consume a net amount of 2 protons for 2 molecules of nitrogen. So 1 proton for 1 molecules of nitrogen. So when we have nitrification followed by denitrification, the denitrification allows to recover half of the acidity that is produced by nitrification. So only half. That means that in case of our process is unbalanced and we have, for example, a very high nitrogen load with a higher nitrification than denitrification, or we have not enough carbon for the denitrification, then we may accumulate acidity, which means that the water will be acidified, the pH will drop. Another example is in the digester, what happened in the digester. So we have the secondary sludge or the primary sludge that feed the digester. And we first have a list of the organic matter. And all the nitrogen coming from this list organics is ammonified. And this ammonification will consume a bit of acidity, a bit of protons. But then this degradation and hydrolysis of the organic matter come with a fermentation process, which produce some volatile fatty acids. So this occurs with the heterotrophic biomasses, and then the methanogen organism will consume this VFA to produce the methane. So here, the production of VFA obviously will also lower the pH as we produce some acids, and then the methanogen will consume this acidity. So it will be normally balanced. But again, if we have an unbalanced process, for example, if we have a too high load of organic matter in our digester, then the fermentation will be higher than what the methanogen can process. So we will accumulate acidity, and the acidity, the methanogens doesn't really like that, and they will also stop working. And also, if we have a too low hydraulic retention time, the methanogens are a bit slow growers. So same thing, the fermentation will go on faster than the methanogenesis, and we may have some souring issue in our digester. So how to model that? In the ISM type models, there is a state variable that is the alkalinity. And for each biological reaction that consume or produce alkalinity, there is an equivalent of calcium carbonate that is accounted for in production or consumption of this alkalinity state variable. However, is the alkalinity a good state variable to follow what happened in terms of physico-chemical reaction, and especially the risk with the acidity of the wastewater. So here there is a graph that comes from the same book that I presented in the previous slide, showing for different alkalinity, the mixed eco pH value. So we can see that with an alkalinity above 50 milligram per liter as calcium carbonate, the pH is quite stable. But when the alkalinity is lower, then the pH drops. Also, we can see here several curves that correspond to different carbon dioxide concentration of our liquor, mixed liquor. So showing that we can reach different pH for the same alkalinity depending on the carbon dioxide concentration. So in other models, the choice was to explicitly simulate the carbon dioxide and all the chemical compounds as state variables. And this is what we do in SUMO. And then the pH and the alkalinity are a result of this of those components that are considered as state variables. So the pH is actually solved at each time step, as Kimberly already mentioned, and the alkalinity is recalculated based on the speciation. So this is the principle of how the pH is solved in SUMO. So at each time step of the simulation, knowing all the compounds concentration, we guess a pH, an ionic strength and alkalinity is calculated. And then we calculate the ionic speciation for each species, chemical species, as Kimberly showed. And then we check if the charge balance is checked or not. And eventually we have to reevaluate the pH. And this is how the pH is solved. So at each time step, we solve everything that should be at equilibrium. So all the fast acid-base reaction, especially. And then once we know the pH, what do we do with this, with those biomasses that are sensitive to the pH? We will have to account for this sensitivity in their kinetic, so in their growth rate. And we multiply the maximum growth rate of the nitrifiers by a function here, which is a bell-shaped inhibition curve. So this is the formula. It depends on two parameters, pH low and high, and it depends on the actual pH that is calculated by the equilibrium model. And we can see this green curve on the graph that pretty well fits those data with this bell-shaped curve, inhibition curve. So that was a small point on how biology can affect the pH and vice versa. And about the gas-liquid transfer. So Kimberly already talked about that. Some of the gases are pH sensitive, like ammonia, carbon dioxide, and hydrogen sulfide. So those curves were already shown by Kimberly. And what should be mentioned also is that, so depending on your process, you may want to strip those gases or to keep them dissolved, depending if you want to recover ammonia, treat or recover sulfide in a way or another, or if you want to keep it soluble to avoid some reasons, then you may have to play with the pH. So keeping them as only the uncharged species will stripped. So here, the ammonia will be stripped only at pH higher than 8, and carbon dioxide will strip at pH below 8, and hydrogen sulfide will strip at pH below 9. But also when you strip those gases, it will affect the pH. For example, if you strip the ammonia, then it will shift this equilibrium between the two species towards some more dissociation of the NH4 plus. Then it will release protons and the pH will drop. Contrary to the carbon dioxide, when you strip carbon dioxide, then you remove protons from your water, and it will shift the equilibrium towards this protons, all the other carbonates forms. Then the pH will increase, and this is a property that is used in some processes to increase the pH. Then it's quite simple to strip the carbon dioxide when we have good alkalinity. And for the hydrogen sulfide, same thing that for carbon dioxide, when you strip it, it will increase the pH. Okay, and then how do we model that in the biokinetic model? So it's not much different than for the other gases. So you may know how the gas transfer is simulated for the oxygen transfer. So it's the same principle. We model as a gradient between the concentration of the dissolved gas and the maximum saturation concentration of this gas in the liquid. And this saturation concentration is calculated based on the Henry's law. And this gradient is multiplied by a rate, which is the liquid side mass transfer coefficient that depends on the oxygen transfer rate. And so this is exactly the same type of equation that for other gases, not pH-dependent gases, except that here you can see that it's the species and not the components, the whole components that will be stripped. It's only the uncharged species that will be stripped and that we should consider in this equation. And so those concentrations are calculated based on the speciation. So Kimberly already mentioned this type of calculations. So here by simplicity, I've shown squared brackets, but in Sumo, we actually account for the activity with a Davis equation that is implemented. So here for the ammonia, we can build a system of two equations. First one is the ionization of ammonia or the dissociation of ammonia, for which we have an equilibrium with this acidity constant here. And the second equation is the mass balance between the total compound and the two species. And from this system of two equations and two unknowns, we can extract the concentration of the two species that depends only on the total compounds, total ammonia compounds, and on the pH, and the acidity constant, the thermodynamic constant. And we can so keep those expression in some tables to solve them. And again, this is how the pH is solved by calculating those ionic species and then reevaluating the charge balance and the pH eventually until everything matched. And so as Kimberly showed already, this speciation of the different species will eventually lead to some precipitation or dissolution. And in wastewater, it's mainly phosphorus precipitates that will occur in the context of anaerobic digester, sludge treatment, or side stream. It may be unintentional or for phosphorus recovery. And it's favored by high concentration pH and temperature, as already mentioned. I wanted to show you an example of this configuration in SUMO, which is an MLE configuration, so with a primary settler, an anoxic reactor, an aerobic reactor, some recirculation, a secondary settler, and then a digester, so that will be fed with primary and secondary sludge. In this digester, in this simulation, all the precipitation reactions are modeled. And what we can see that we have quite a bunch of brushite and struvite here in the digester. So that can lead to some scaling of the pipes and of the pumps and a lot of issues related. And what should be also noticed here that the phosphate concentration in the digester is pretty low. And what would happen if we do not account for all those precipitates and the pH in the digester? So I've voluntarily set to zero all the kinetics, all the precipitation kinetics here, but in SUMO with the default parameter, it's not possible to do that. The precipitations are always calculated in the digester. We will see why. You will see why. So in this second simulation, without any precipitation, we now have almost 200 grams of phosphate per cubic meter. And concerning the mass flow that returns with the sludge liquor, we can see that when we simulate the precipitation, we have 5.4 kilograms of phosphate per day. And here, without the precipitation considered, it's 19 kilograms of phosphor per day as phosphate. So coming back at the head of the treatment plant. So that's quite a lot of amount of phosphate that needs to be treated again. Well, it's just a simulation, but if you do not consider precipitation and pH, then it will lead to false results of how your process behaves. And at the effluent, also, it will change the predicted concentration. So you may not match your data if you do not consider the precipitation in the digester. So I will go pretty fast on those because Kimberly already shown that how the precipitation is simulated. So with this ionic product minus the solubility constant to know if the precipitate will precipitate or will dissolve eventually. And that is cubed or squared depending on the precipitate. And this is, so we follow the publication from Koutsoukas from 81. And to increase the precipitation, we should ensure that we have enough chemicals. And so we have supersaturation, especially if we want to recover the precipitates. And also the pH will affect the precipitation. Here, in the case of the struvite precipitation, the species that is involved is the phosphate ion. So meaning that we need phosphate ion. So we need a quite high pH, above 8.3. But for some other forms of precipitates like brushite, which is a hydrogen phosphate ion species that is involved, then it requires a lower pH. So you see here, so yeah, it's around 7, so not too high to not have too much competition with struvite. And for amorphous calcium phosphate, which has 2 molecules of phosphate ion per molecule of precipitate, then it requires a very high pH, above 8.5. So how do we reach that? By adding more chemicals or by eventually stripping the carbon dioxide. And eventually we want to mitigate those precipitation, and the use of some metal salts may help. And this can be found as a mitigation strategy in the digester, and it will mitigate actually 2 different problems in the digester when you dose iron. And this graph will show you how. On the x-axis, you have different loads of iron that is added, a different dosage. And on the y-axis, it's the different precipitates you may form. When you dose a small amount of iron, you will first mitigate the sulfide, which will precipitate as ferrous sulfide. So it will not be pyrite, because pyrite needs more time, but it's an amorphous phase of it. And once all the sulfide has precipitated as ferrous sulfide, so you see here this hydrogen sulfide is almost 0, then the additional iron will precipitate as vivianite with phosphate. And this will actually mitigate the issue of struvite precipitation in the digester. Usually we prefer precipitation of vivianite than struvite, since it won't scale in pipes and pumps like struvite does. And this is what we have implemented in SUMO, and that pretty well represents this competition between different precipitates that may occur at the same time, but with different concentration of iron available. And this will link with the chemical treatments that we may find in the waterline too. And I will use for that some data that come from a fact sheet I've worked on, and that has been published in 2023 by the WEF. So you can find it on the web. And this table comes from it. So on the waterline, we made those some aluminum, ferric, or ferrous salts in order to precipitate or to remove phosphorus. And those salts, for most of them, so I won't comment about the chemical dose. You can find a lot of information in the fact sheet. But what I want to comment is this alkalinity impact. So you see minus, 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 1 plus, and a minus here for ferric chloride. That is pretty well used. And this minus sign means that when you use those salts, it will consume alkalinity. Why it will consume alkalinity? It's because when you dose ferric chloride, it will precipitate into hydrous ferric oxides, and it will release 3 protons per mole of iron. So it has to be accounted for, as it will affect a lot the pH eventually. So you may have to add more alkalinity to counterbalance. And this is on those hydrospheric oxides that the phosphates will bind to, and will be removed from the dissolved phase of the liquor. But Also, you can see here the last row. It's an optimum pH range. For all of those salts, there is this pH range around 6 to 7 that is optimal. And we can also see it on this graph that show depending on the pH after the coagulation, the residual soluble phosphate. And we have the lower phosphate residual for the pH around 6 to 7. So that's what was said also in this table. And then with lower pH or higher pH, the chemical treatment is less efficient. And this is actually because those salts, hydrous ferric oxide or hydrous alum oxide for aluminium, will redissolved as a monomeric form of metal hydroxide at lower pH or at higher pH, that this range. And actually, you can see comparing those two graphs that aluminium is even more affected by the pH than iron. So yeah, that was what I wanted to present you, how we account for all of this very complex system in simulation software and how everything is impacted by pH, the biology, precipitation, gas transfer, and the chemical treatment. So it's really important to account for all of these reactions. And if I have few minutes, I may show you in sumo again how the biology may be affected by the pH and how it affects the pH. So I've taken in sumo this MLE example from our example list. And so, yeah, to keep it simple and in few minutes, I am in a simulate tab, and I've chosen two parameters from the influent to appear here. So the total Kirschdal nitrogen concentration in the influent and the alkalinity concentration in the influent. So I've run a steady state start simulation of 1 day, showing that what happened. We have pretty good nitrification and denitrification occurring in this example with an ammonia concentration below 0.5 and nitrate is around 4. So that's pretty good. The pH is pretty stable, around 7, a bit higher than 7, that's good. And the alkalinity, at the influent, we have 350 milligram of calcium carbonate. Then in the anoxic tank, only 286, and in the aerobic tank, 255. So this is the loss of alkalinity because of the nitrification. But everything is good. We have a good pH, alkalinity is still high. That's good. Then I will turn into advanced mode, and I will vary the total Kirschdal nitrogen from the influent between let's say 10 milligram per liter to 100 milligram per liter. And I will take 10 steps and run a steady state analysis. So it will analyze the sensitivity of the model to this variation of the total Kirschdal nitrogen at the influent. So each step corresponds to the steady state results with a different total Kirschdal nitrogen. And what we can see here is until Kirschdal nitrogen around 80, while the alkalinity becomes lower and lower, and especially in the aerobic tank. And then it's really low, around 50 milligram of calcium carbonate. Well, what happened with the pH? we see the same thing, around 80 milligram of nitrogen per liter in the influent. Then the pH drop below 6.5. And the consequence is that we lose at the same concentration, we lose the nitrification. Here, the ammonia start to go up on this curve. And if we look at the nitrate curve, we can see that until 80, the nitrification was okay. But we can see that actually the denitrification couldn't really occur from 40 kilogram gram of nitrogen per cubic meter, since probably not enough readily biodegradable carbon was available anymore for the denitrification. So the nitrates start to accumulate, and then everything broke. We do not have any nitrification, neither denitrification. So this is the impact of the nitrogen load. And just quickly, if we come back to a reasonable concentration of nitrogen for municipal treatment, but just show if we have a soft water with a low alkalinity at the influent. So it's not a very high ammonia load, but just a soft water at the influent. We take 10 steps. And so here we can see when the water is too soft, we have, maybe I should have taken an even softer water, but we have a less efficient nitrification. And so the alkalinity, the residual alkalinity when it was 150 at the influent, the residual alkalinity in the aerobic tank was actually around 60 milligram of calcium carbonate. So it was pretty low. So yeah, I should have chosen maybe 100 instead of 150 to really demo it here, but you can already see what happened with the pH. So this is some points on which we have to be careful when we have nitrification, good nitrification. If we have a bit too soft water, even with a good carbon to nitrogen ratio, then we may have some acidification issues. So I think I've said what I wanted to say today. If you have any question, I think Luz will take over for the questions.
Yeah, we now have some time foreseen for questions. JD, do you want to monitor those?
Sure, I'll be doing that. Currently, some people have been writing inside the chat, and I think Kim has been proactive in answering one of the questions. Just to get the wheels greased a little bit, maybe we can just state that question, and Kimberly can say our answer out loud for everyone to benefit. So the question was from Marjan. She said, can you please briefly explain about when microbiology and biological kinetics can be applied? And
thank you for the question, Marianne. But so actually it's the basis for the physico-chemical model. It builds upon the activated sludge model. So in the activated sludge models, that's where we have all the biological reactions. So this is these biological reactions also tell us about the different components there, like the nitrate, ammonia, and then the physical-chemical model builds on or alongside this activated sludge model. So at each time step where it is solved in the activated sludge model, the physical-chemical model runs its own thing and solves, for example, the pH and the activities, and returns it back to the activated sludge model. And also, I think the examples that Helene showed also answered this question, how the biology and the physical chemistry are all highly interconnected.
I maybe had a very short follow-up question on that. Is this ASM and physical-chemical model integration done for like every basic ASM model you use, or is this a special type of ASM model you need to use?
Well, in Sumo, it's built in together, but in the traditional activated sludge models, it's not included. So we have calculations for the alkalinity, because as I said, like initial goals for developing those models is different to what we use these models for now. So that has changed. So these are like modules that you can connect. That's very simplified. Like you can connect to your activated sludge models, so you can also take into account this pH, precipitation, gas liquid transfer, all those physical chemical reactions.
We have a new question coming in from Pompilia, asking, is modeling the alkalinity but not pH enough when we only model nitrification, denitrification, worried about phosphorus? We need to worry about pH.
So, well, in the ASM publication, it's mentioned that this alkalinity will predict a risk of pH drop or acidification. So modeling only alkalinity, it gives you an indication if you have a risk to have a pH issue or not, but it's less accurate than modeling the pH and applying this pH impact on the biomasses and on the other physico-chemical reactions. So I would say that probably most of the time, if you do not have a pH issue, well, it's probably sufficient to simulate alkalinity. But if you have more intensive processes, then maybe it's good to have more accuracy. As Kimberly also you show it in the first slides, I think that no, the objective, the goal of the wastewater treatment processes are different than that it was some decades ago, and we need to have more accuracy about those pH issue because of that.
Wonderful. Thank you for your answer. I'm sure. Oh, there we go. We have a new one. The question is from Hossam, and he asks, if the outlet NO2 is relatively high, this can be attributed to DO set in the aerobic zone or the volume of the anoxic zone, but no improvement is shown. Oh boy. Maybe denitrifies bacteria is responsible for that. In Sumo, how do you calibrate denitrification is the question. In the past example, the effect of side stream flow may be negatively affecting alkalinity. So that's more common. I think Hélène would be the one that can take over that question, if you would.
So yeah, is it outlet NO2 or NO3? Well, this is a specific question. Then your set point. So I'm not sure if it's relative to the what I've demoed here or if it's different. If it's relative to what I've demoed here, the DO set point, I haven't mentioned it, but it was 2 milligram per liter in the aerobic reactor, and it hasn't changed. So I haven't take care of it, but whatever the load, the nitrogen load, it was fixed to this value, so it shouldn't affect the efficiency. But of course, this is something that would be important if you have different nitrogen load to account for this aeration needs. So yeah, then I think it was relative to this example. And the side stream flow may
it was
be
an
negative.
O3, not an O2.
Okay.
Apparently.
Yeah. I was puzzled to yeah. Okay. And yeah, sure. So here this if you talk about this recirculation, so it will recirculate the nitrate that are produced with the nitrification. So for the denitrification, yeah, of course, maybe with the different loads, we should have um, modify the recirculation or to have a better efficiency. Yeah, that was not in the scope of this small examples, but that's right.
Thank you. And another question from our John is how much, you'll love this question, how much these models and results of simulation are accurate and translatable for real operational data in facilities? So I guess it's a big question.
Yeah, that's
But it's
also
quite
a
an
very
important
good,
one.
that's a very good, really important question. First of all, I would like to say that physical-chemical models, the aqueous phase chemistry, for example, at which the precipitation, the gas-liquid transfer are also dependent on, these are well established. These are, you have also several models, standalone models available for these physical-chemical models. Maybe you're familiar with Mintec, Frixie. So this the models, for example, the aqueous phase chemistry, I would say that they are accurate. But the combination of the physical-chemical models together with the biological models, that's quite complex. But these have been also models that have been calibrated and validated in the past. So for example, for precipitation models, there are studies that have done this. If you check the scientific and technical report on the generalized physico-chemical modeling framework for wastewater treatment, there you can see the examples, plant-wide examples, like full-scale examples where this have been applied. Of course, calibration and validation is important, and it's also much more complex because since you have to measure much more, measure things that you didn't measure before with the normal activated sludge models, but these models have been validated and calibrated before. But of course, you always have to calibrate and validate it for each case.
Hélène, do you have something to add to that? Based on your experience working in the simulator? No? Yeah.
That was a good answer from Kimberly. We have quite some experience with some full scale application, and that's working pretty well. Yeah, as Kimberly mentioned, it's pretty well established thermodynamic reactions. Maybe we could just specify that for the precipitation, it may be a bit different. It may differ a bit more depending on the on the type of wastewater. Well, for municipal wastewater, no, it's working pretty well. But that's, yeah, the thermodynamic constants are sometimes for some of the precipitates less established, but for most of it, it's good enough to predict what we want to simulate, so to model.
Okay. We're getting another question. Would the chemistry calculations or principles presented by Kimberly also apply to desalination to estimate the scaling propensity? So systems outside of typical wastewater treatment.
Yes, definitely. Because actually, like, these physico-chemical models that we use for wastewater have been much more used for other systems. So I think for desalination, it can be more easily applied. Wastewater it's more complex because you have biology, but with the desalination, you have less issues with that. So yes, definitely, especially the aqueous phase chemistry calculations, you can always apply it.
Yes, so this scaling risk
I might have a
in
question
this kind
myself,
of,
if that's okay. Yeah.
yeah, so in this sorry, in the arrows, for example, or in the process unit that are used for desalination, we used to calculate some scaling risk, and it's exactly the same equation that Kimberly shown, to calculate if it will if the conditions are super saturated for a precipitate or not. So we compare the ion activity product with the thermodynamic constant, and then the scaling risk is calculated. It's done like that in all the simulation software.
So the chemistry holds wherever you are. It's chemistrying still. So that's nice. I have a question in terms of like how much does adding like these chemical equilibria into your model affect identifiability of the model? Does it become more difficult to calibrate or easier to calibrate, but in the wrong way?
Well, it's a separate problem because
Okay.
So you have your biokinetic model in the matrix with the differential equations, and then you have your equilibrium model. So the equilibrium model has to be solved. I'm not sure. I think it won't affect the identifiability of the biokinetic model, but for sure it slows down the simulations. Yeah, because at each time step you have to solve this equilibrium of all the species and the pH. Yeah, so it slows down.
Gotcha. Okay. And another question that we have in the chat is there, well, what I'm getting from the question is there an alarm for alkalinity destruction in sumo when when the alkalinity balance gets too low?
No, but that's an idea to add it. Yeah, we actually have some alarms when the MLSS is too high, when the DO cannot be matched, cannot. Yeah, so that's an idea to. Well, for the digester, for example, we have an alarm for that, but it may be intentional since a digester process unit may be used as a fermenter, which is also quite conventional to have first fermentation step and then methanization step. But yeah, I will keep the idea. It can be useful.
If anyone's been holding out on a question, now's the time. We're all through with the existing ones.
If there's no more questions, I would just like to show this. It's a small spoiler for our next MIA Academy session, which will be all about data handling, and the date is to be announced. So follow us on LinkedIn for more updates. And then I would like to end this session by thanking Helene and Kimberly for being here and giving a very nice explanation on physical-chemical models. And I would also like to thank Jean-David for moderating the question sessions. And thanks to everyone for joining and listening to us. And hope to see you in the next sessions.
If I may add, I will also add the link to the YouTube playlist with all the recordings. So you will be able to see this recording and all the past sessions over there as well, very shortly.
Okay, thank you.
Thank you very much.
Bye.
Thank you. Bye.
Bye.